So, what? So what I've got here is just a string that's suspending a paper clip with a really, really strong magnet. Okay? So this is a situation where it's like force at a distance. So you really?
Witchcraft.
Okay. So if I take my hand,
Wait a second. What is happening?
Witchcraft.
this is just a really strong magnet.
Burn him.
Okay? And I've got the paper clip tied to the string. Okay? And magic. There's magic is in the gaps.
Putting the magic.
I'm vowing that. North magic, south magic. Okay. Now, so what are the forces acting on the paper clip?
Gravity.
Gravity's trying to pull it down. That's one. The magnetic force pulling it up. And there's a third one.
Tension's pulling it down.
The tension. So this is like magnetic buoyancy. No, it is. Well, but so that field is obviously there, but if I move my hand through it, nothing happens. So what does that tell you about my hand in terms of the interaction with that magnetic field?
Your hand has no effect.
My hand is not magnetic. My hand does not influence that field at all. So I can move my hand through it. Obviously, nothing's going to happen.
What happens if we stick in another?
Well, now if I move this, okay, you'll notice that I can move the paper clip with it. Again, witchcraft. Okay, but there's also a limit to how far I can move it. So if I move it too far,
Oh my god.
now getting close. So notice that as I move it, notice that that paper clip stays just a little bit left of that magnet. So even if I move it like this, that position of that magnet or the paper clip relative to the magnet stays in the same place. Why does it stay there? You would think if I moved the magnet that position would change. So why does it stay in that one particular spot?
The pole magnet's that way. It's on the
Magic,
side.
okay. So you've got field lines that are coming out, right? So basically what's happening is that I'm turning that paper clip into a magnet, okay? That one attracts it. So if I pull it away, this is no longer a magnet. But if I put that up there,
So you broke the magnet?
well, the problem is I got that set to like
How?
very small.
He's a witch.
Is it one specific spot?
Yeah. Yeah, because if I try it over here,
He's a witch.
You can't put it closer?
You would definitely give a
The
person.
string's not long.
This is the most conclusive evidence.
Well, no, because look, it has.
but yeah, I have to have it in one specific spot.
Magic. Magic.
If we had to say the
Witchcraft. Burn him.
What?
I
You are so gonna hate this test. This,
already hated the last.
oh, it's you're gonna hate this one worse. Okay.
Okay, wait, so can you explain to me how come, even if you were to, right, because you can put it closer to the magnet.
Yeah, like I can put it right there.
The pole's not.
But why?
It's not attracted to the side.
Use another
It's
magnet.
attracted to the pole, which is on
Are we
the
gonna
side.
Well, if you put it on the other side, you know.
What if you put the
Yeah,
pole
wait,
closer?
why does it only float at one point?
Yeah, flip the magnet.
Now, if I try and put it here, hold on, let me lower it down a little bit. Okay, and I'll spin the magnet a little bit. Okay,
How does that
Oh,
help?
wait, yeah, it's on the,
Yeah.
so if I do this, okay,
so the pole is on the.
Okay, the pole's on the
Yeah.
side.
Yes.
okay,
So
Now-
we tilt it.
you got this. Now notice that this tension has gotten stronger. Why? What did I do? I lowered this.
The magnet's gotten closer to the.
Yes, okay, it's more of it's in that magnetic field. Now, I'm gonna do this, I'm gonna rotate this. Now, so even now, like I can't get this to stick on this side. Because what happens is that this is such a strong magnet When I bring that close, it actually turns this bar into a magnet. So I can only put this on in one direction. Because if I try and do it like that, I can't I can't push that on there.
Use another.
But if I flip it over, then it can't, because it's such a strong magnet, this becomes its own magnet.
Can we
So,
put two of the magnets together?
oh yeah, that's bad. So the reason that that exists is only in one place, because of the fact that that's just where that strongest interaction occurs, because this is turning into a magnet as well. So I pull it away, it moves, but if I reach a certain distance,
Oh my gosh.
it falls. Why?
Not
It
enough
needs
force.
more.
Yeah. So what wins? Gravity. So let's have a quick review. If I gave you this problem and said draw all the forces on the magnet and their directions, what would you have?
Force straight down for
That
gravity.
was on the paperclip. On the paperclip.
Force tension.
So you got gravity acting straight down. The force from the
Tension.
tension, right?
Acting
Going
with the
like
strength.
this. So you got gravity going like this. Which direction is the tensional force acting? Up or down?
Down.
Down. So gravity's trying to pull it down.
Anti-gravity.
Tension going like this. So then you have the attraction from the magnet going up.
Buoyant force of the air from the amount of air the magnet displaces.
No, it would be on, that would only be on the paperclip.
Oh yeah, that's a magnet.
Okay.
Technically, it is a magnet.
So if I move it too far, though, like you said, what's going to happen?
It'll fall.
Just leave it right there.
There's going to be a big net
Okay,
force.
we can do it just like that.
There's so much space.
The net force is going to be too big in
Okay.
the
It's
paper.
not that much.
It's
funny.
magic.
Okay. Now let's see even more magic. So come over here.
Magic.
So you need to come over here so you can actually see the painting.
Guess what's now?
It floats.
Yeah.
Okay. So I've got a pretty strong magnet right here,
You should like have a casing of.
and
sprinkle
Put a,
oh, I'm just gonna sprinkle it over the top, right?
Put a Ziploc bag on it or something.
Look at that.
Witchcraft.
Okay.
Black powder. I'll cast black powder in your lungs, Cohen.
Shush.
What does that even mean? How are you even gonna do
I
that?
don't even know what that means. Okay, now if I give this a little bit of a tap.
Magic.
Okay. So
Weigh 'em with a.
okay, so I got the magnet here. So the cool part about the filings is that this is showing that it's, everybody tends to think of magnets as being like one-dimensional. So, but it's not. So these magnetic field lines are going around in all directions around it. It isn't just in one plane. But what this does is that it shows you that the field, just like the ferrofluid, the field isn't continuous. That's why when I tap this, those iron filings align and follow suit within specific lines. If this was like gravity and you tap it, you wouldn't see any lines. But because of the fact that this is showing up in lines, that tells us that unlike gravity, this exists still as a field, but not a continuum. And even like with this, how this is sticking out like this, like upwards, it's because those field lines are coming out like a fountain coming out in all three directions. Okay,
So why is it lines and not
because of the fact that it has to do with the domains, and when those domains line up and only produce that magnetic field in one particular direction. Okay,
Continuous.
now over here. Okay, so I've got a tiny little magnet here, and if you've never actually tried to navigate with the compass, it's kind of cool. So this compass has like a little blue, it's a little like floating.
Nothing's happening.
If you look at the top of it, it's like two triangles that meet in the middle. And one of them had, in this particular compass, that end is coded blue. So if you want to figure out which direction that you're going, you just hold it up, and then you spin it around until the north lines up with that. So as soon as I get this, and that's pointing in this direction, I know that is magnetic north. But it's actually pointing towards the south pole of the magnet that's inside the Earth. Okay? So what's happening is that inside the Earth there's this big massive magnet. And this little magnet right here is lining up with that magnetic field. Okay? Now, what I'm going to do is I'm going to put this here underneath this wire, which right now has no current flowing through it. So what I'm going to do is I'm going to briefly turn this on. And when I turn that on, what you'll see is that, and if you can see this, as soon as I turn that on, that compass went from pointing this way, and it turned and pointed to the east. I turn it off, and it comes back, lines back on. So I turn it on, whoop, goes over there, turn it off, it lines back up. So what that tells me is that there's a magnetic field that's being created by the wire. This is going to be the first example of what's known as the right-hand rule of magnets, and it's always the right hand. So, and I'll diagram this up on the board. So to figure out the direction of a magnetic field, okay, it's called the right-hand rule. The first variation on this is pretty simple. What you do is you point your finger in the direction that the current is moving in the wire. And when I say current, I mean Ben Franklin current, not electric. Don't kill the messenger. Otherwise, we'd have to use the left-hand rule. So we use the right-hand rule. So there's a current that's flowing through this wire. So what I'm going to do is I'm going to take my right hand, hence the right-hand rule. And I'm going to put my finger or my thumb in the direction of that current. All right? Then you take your fingers on your right hand and you curl them in this direction. So as that current is going in this direction, the magnetic field is going around the wire like this. This is why that magnet turned and went like this. Because of the fact that the current's going this way, you wrap your hands like this, so the current is going, if you imagine this wire being embedded in the table, the magnetic field would start and it would come out of this side of the table and it would go in on that side of the table. Now, if you reverse the current and the current would go in the opposite direction, then you would put your thumb in the direction that it goes. Then you would wrap your hands like this. And if you reverse the current, then it would go in to the table on that side and out over here. But the same rule applies. If I move this wire and move it up here and I turn it on, what's going to happen to the strength of that magnetic field that external compass is going to experience? It's going to be much weaker. If I have this way up here, basically nothing happens. But if I move it closer and closer, then I get more and more deflection based upon that magnet. So if you look at this, what do you think is going to happen if I increase the amount of current in the wire? Do you think the magnetic field is going to get stronger or weaker? Stronger. So there's a direct relationship between the current in the wire, more current, stronger magnetic field. I just put it up in the front, in the normal tray. Thanks, Bethany. So there's a direct relationship between current, but an inverse relationship with distance. The farther you are, the weaker the magnetic field. More current, more magnetic field, more distance, weaker magnetic field. Got it? Good? Now, let's go.